Welcome, ladies and gentlemen. My name is Mark Schinkel. Today it's my pleasure to welcome all of you in the name of CIMAC to today's Tech Talk special about emission reduction. Our warm-up towards the Congress in Busan next year is going to continue. Today we are going to hear 4 presentations from Mr. Mehrabian, from Mr. Etzien, Madam Lehtoranta, Mr. Kock, and today's moderator will be Mr. Ghetti. As usual, I have to make some legal remarks. The Tech Talk special, with the Tech Talk special, CIMAC would like to offer a platform for exchange. The presentations are an information offer of the respective author and or the companies, and thus do not necessarily reflect CIMAC's opinion. On top of that, I have to make the remark that this session will be recorded and be put online for later use. And I want to encourage all of you to ask questions in the chat. Please also feel free to do so during the presentation. Our moderator will review the questions and ask them to the respective speaker. With that being said, I can already hand over the voice to Mr. Ghetti.
Okay, thanks, Mark, for this nice introduction. My name is Stefano Ghetti. I'm a director at FEV for program management. And today I will moderate this second CIMAC Tech Talk regarding emission reduction. So 2 weeks ago was the first session. Today is the second session. As Mark introduced, we have today 4 speakers. And we will start with Mr. Ramin Mehrabian from LEC. So he has a PhD in process engineering, and since 2019 is working at the LEC as a senior researcher in integrated system section. And today he will speak about optimized integration of an SCR-based aftertreatment system into a multi-cylinder large diesel engine. So Mr. Mehrabian, the stage is yours. And at the end, I will pose some questions. Please use the tool for the question that I will then be able to do the question at the end. Thanks.
Hello, everybody. I hope that you're seeing my presentations. Did I correctly show the slide? Yes,
we can see it.
Yeah. Good, thanks. Good, so then again, hello, everybody. Have a nice afternoon. As it was announced, I would like to show some results and also our project together with the AVL, Umicore, and TU Graz, which was about the integration of a DOC DPF SCR after treatment system into a multi-cylinder large diesel engine. In my presentations, I will show you some introduction and motivations about this project, the exhaust after treatment test system, and also catalyst specifications which we had, and I will show you some results afterwards, and then at the end the conclusions and the summary. About the motivations in this project. As you know, as a result of a continuously stricter emission limits, NOx and particulate emissions of current large diesel engines must be considerably reduced. Therefore, an advanced DOC DPF SCR exhaust after treatment system to fulfill ultra-low emissions has been developed and demonstrated in this project. Our targets for tile pipe emissions were as the following, like 250 milligram per kilowatt hour for NOx, PN 23 we choose to be less than 10 to the power of 12 number of particles per kilowatt hour, C of less than 30 milligram per kilowatt hour, CO less than 800 milligram per kilowatt hour, and particle mass or PM 10 milligram per kilowatt hour. As for just your comparisons, I show here some let's say legislations limitations like stage 5 or TE-Luft or 45 BMSV parameter limitations for these parameters. As you can see, we always use the lowest in each category for our target in this project. Regarding the test cycle which we have used in this project, a non-road steady state test cycle with 8 modes has been chosen for these projects for the evaluations, the exhaust after treatment system. It has 4 modes. It has these 4 modes with the rated speed and 3 modes with the intermediate speed of the engine, and of course the idle point. And with these corresponding weighting factors to calculate the emissions at the tailpipe. This is the arrangement of the test system, and measurement points are schematically shown in this slide. Here, the exhaust gas of one engine cylinder bank is used for the exhaust after treatment systems because of the size and also sizing of the catalyst and also the limitations of the space in our test rig. So that means the half of the exhaust gas goes through the exhaust after treatment system of this engine, and as you can see, we use after the turbocharger, we use actually the smoke meter and marker soot sensor to measure the particle emissions or the soot at the engine out to more or less monitor these emissions, and then going to the DOC DPF reactor where we measure the temperature as well as pressure and also the pressure drop over this unit. And then the exhaust gas goes to the urea dosing and mixing unit. We also monitor the pressure drop over this part, and also then finally going to the SCR reactor where we measure at different positions temperature inside the SCR catalysts and also the pressure drop over this unit, and then finally going to the particle counter finally doing some sampling for the particle counter and smart sampler to measure the particle numbers and particle mass at the tailpipe for evaluation of the measurement of the performance of the exhaust after treatment system. And of course, at every critical point, inlet of the DOC, outlet of the DOC, and outlet of the DPF, and also upstream DOC and also downstream of the SCR, we do some sampling to measure the exhaust gas composition with 2 measurement devices with this conventional gas analyzer system and also with FTIR to know how is the performance of the SCR and also DOC DPF. And here again a picture about the exhaust after treatment system. The engine, as I said, the exhaust gas of one cylinder bank goes to the DOC DPF reactor. Here is a picture of our test bed. This is the DOC DPF reactor, and then coming to the dosing and mixing unit. Here is the dose, and 3 nozzles for dosing the urea, and then this is the mixer, and then it is far enough upstream of the SCR, the mixer is positioned, and then going to the SCR reactor and then to the tailpipe. And here, for example, just as an example, here is the measurement sampling positions for doing the sampling for particle counter and also with the particle mass measurement smart sampler to measure the particle mass. Here, briefly, some information about our multi-cylinder engine test rig. The core of this test rig is a 12-cylinder engine with 75-liter total displacements. It can be used to investigate and evaluate different configurations, hybrid depopulation, propulsion, exhaust after treatment systems, as it was used in this project, for example. And also it can be used to evaluate and also analysis the fuels, different type of fuels, from conventional to hydrogen, methanol, and also ammonia. Here in this slide and in this table, the engine out emissions are shown for each duty cycle point, the discrete mode cycle. And also the total cycle values are shown here for engine out NOx, CO, and HC, as well as the PN23. And these are measured following the 40 CFR regulation part 1065 to calculate these emission cycle values, the whole cycle value emissions. Then here specifically some information on the DOC and DPF, where we see the volume of this, the DOC, and also the volume of the DPF, as well as the number of cells, and also the platinum group metal unloading of DOC and DPF. On the right-hand side, you see a picture from a sections between the DOC substrates and DPF substrates, where we put our different thermocouples in different positions, as well as these thermocouples inside the DPF in different positions. Here is the, it's not so clear, I guess, from this picture, but here is the positions where we measure the temperature, the pressure between DOC and DPF, and here is the sampling tube where we measure, where we do the sampling of the gas sampling and send it to the gas analyzer to measure the gas composition. And here's again the schematically showing of this DOC and DPF reactor. It's the 4x4 DOC array, and also 4x4 DPF arrays. Here the same for SCR, the volume of the SCR catalyst, cell per, the number of cells, and also a picture from front view of the 3x3 array for SCR substrates. These are the supporting tubes where we put the temperature, the thermocouples inside the substrates to measure in different depths the temperature inside the substrates. And here is again pictures downstream of the mixer, and also here you can see supporting tubes to measure, and also the thermocouple to measure the temperature at the inlet of a SCR or downstream of the mixer. As the first set of results, I would like to show you the NO2 formation over DOC DPF. Here for each duty cycle point, C1 to the C7, you can see the NO2 to NOx ratio, upstream DOC, upstream DPF, and downstream DPF. And as you can see, the NO2 formations actually mainly happens due to the DOC. And an ideal NO2 NOx ratio up to 55% for all duty cycle points are achieved. And this is actually due to the appropriate DOC DPF design and coating. The overall performance of DOC DPF was well. We could meet the target, the project targets for CO, HC, and PN23. As you can see, here's the PN23 tile pipe emissions. Here is the engine out PN23, and the same is here for CO, engine out, tile pipe, engine out tile pipe for HC. As you can, if you compare these numbers for the tile pipes with the targets of in our project, all of these targets are fulfilled, and it could and also this is the reductions of the CO, HC, and PN23 for each of due to the good performance of the POC and DPF. Here, I would like also to say that the SCR is also performed well, and we could reach our target to meet the NOx at the less than 250 milligram per kilowatt hour. As it is shown here, this is the total cycle value. Engine out 10, as I show in the first table, 10 milligram per, 10 gram per kilowatt hour, and we could reduce it up with a 98% reduction, and we could reach less than 250 milligram per kilowatt hour at the tile pipe. And additionally, you can see the performance of the SCR for each duty cycle point, for individual duty cycle points, and they have been measured. All of them have been measured at the ANR less than 1.05, with the ammonia slip less than 50 ppm. I have to mention that for these 2 points, C1 and C5, due to the limitations of the dosing quantity, we could not measure the performance of the SCR at the ANR bigger than 1. I mean, we could not dose the adequate quantity of the urea to reach the ANR bigger than 1. Therefore, in our test system, the measured parameter, the maximum measured DNOx ratio was 92% for C1 and C5. And therefore, since we wanted to know what the performance of these C1 and C5 load points at the ANR higher than 1, this is a meaningful ANR ratio, we used the Umicore SCR model, the simulations of this proven model of the Umicore for the SCR just for these 2 points, and we could, that means instead of 92% DNOx, we use the simulated value of the 95% and 97% for C1 and C5, and then finally this cycle value for the whole cycle has been calculated. And here, the pressure drops over each part of the exhaust after treatment system are shown for every duty cycle points. Here is over the DOC DPF, as is expected, it is the maximum pressure drop, and then over the mixer is more or less nothing, and then over the SCR, this light blue color, and you can see the maximum back pressure of 50 millibar at engine full load has been with the maximum volume flow clearly is observed, and it's proved that maximum 50 millibar back pressure we have with this after treatment system. And coming to the last slide, and to do this and to sum it up, an advanced DOC DPF exhaust after treatment system for high-speed large diesel engines has been successfully tested in this project. It fulfills the most stringent emissions limits for NOx, HC, CO, and particle numbers with a very acceptable, very good pressure drop, also, what is still ongoing, we are now further investigating the PN10 and also PM measured parameters because we need some further investigations, and these informations will be published soon in the form of a paper. Good, Mr. Ghetti, I'm finished with my presentation.
Thanks a lot, Mr. Mehrabian, for this very interesting presentation. So we got here some questions from the audience. I remind all of you to push your questions in the tool, because then I could raise this question. So I have here a couple of questions that are coming from the audience. So the first question was in regard to the substrates. Why do you use a silicon carbide DPF filter and not a cordialite? Can you make some question to this? Some comment to this?
Could you repeat again the questions regarding the?
Use a silicon carbide DPF filter and not a cordierite.
Actually, this was the design to have a less pressure drop. As you see, we could achieve this with this system, 50 millibar back pressure.
Okay. Okay. Thank you. Then we have other questions in regard to the NH3 sleep. So one question is, what was the limit that you set for your NH3 sleep? And then together, is 50 ppm of ammonia sleep too much? Or so do you have a certain limit that you set yourself?
I mean, for the ammonia sleep, we set the 50 ppm limit in our measurement system and in our testing system. Of course, we not in all of these load points we reach the 50. I mean, we are always something about 20, 25, but to be on a, let's say, safe side, we set at the 15 ppm ammonia sleep.
Mm-hmm. Okay. Okay, then we have another question. So for a wall flow particle filter, one would typically expect filtration efficiency above 97%. So you showed a significant lower performance. Can you comment on this?
Yeah, we could achieve the 83% for PN23. This was actually the performance of this DPF. But I guess this is a, let's say, compromise between the efficiency and also the pressure drop of this system. And also, I would like to say that it may also referring to the soot cake from these soot cake formations of this DPF, because these measurements done with more or less very few operation hours, and I guess after a longer operations we could have better soot cake formed and better filtration efficiency.
Okay, thank you. So maybe one last question from my side. Have you seen any effect during the dosing on the tailpipe particle emission? So have you seen something in this direction?
Yeah, due to the dosing of urea, actually it has an effect on particularly on the particle numbers. I would say the particle number PN10, not PN23, clearly a trend that's by having some urea in the system, the PN10 increases in regard to no dosing or less dosing.
Okay, very good. Maybe my last question, then I think we can close for this chapter. Have you done some modification or optimization in the base engine calibration, or it was just taken over?
No, we actually at the beginning of the project we defined that the engine should, I mean, it was defined together with the UMICOR and also AVL that what could be the requirements of the engine, and this was the requirement of the engines. We should fulfill the NOx 10 and PN10 was 15 milligram per, I mean, PM 15 gram. Actually, so PM 15 milligram per kilowatt hour, and this was the minimum requirements for the engine, and we did not do any special modifications on the engine.
Okay, thank you, Mr. Mehrabian. So thanks a lot for this very interesting presentation. So now we can thank you. So now we can switch to our second speaker. So his name is Uwe Etzien from University of Rostock. He is a research engineer at the Institute of Piston and Combustion Engines, and he will present today something in direction investigation on combined scrubbing and particle filtration technologies for maritime application. So, Mr. Etzien, so the stage is yours.
Okay, I need to change. Yeah, thank you for the introduction. I just try to share my screen.
Okay, now we can see. Perfect.
Now you need to see the Where is it? No, you're seeing which one you're seeing the.
I think you just switch the two monitor on top. So Anzeigen, Einstellungen. Then you have to switch the primary screen with the second screen. Anzeigen, Einstellungen on top.
This one, yes. Now it's the right one, right?
Now we see still the PowerPoint.
Yeah.
So we see the full screen mode.
The full screen mode.
No, we don't see the full screen mode. We see just the PowerPoint.
Wow.
It's the right screen. You just have to switch to full screen mode.
Presentation mode, yes.
Yeah.
Oh. On Friday it was easier.
Maybe if you press F5 to go to presentation mode directly.
I am in a presentation mode on another screen and I just can.
Okay, now it's correct. Now we see. Okay.
Okay, then I'll just leave it like this and I turn my camera off. Yes. Yeah. Thank you again for the introduction and also hello from my side. I'm glad to be able to talk about our research project called SARUS, and today's presentation has the title Reduction of Particulate Emissions from Shipping, a necessary task for the near future. In the next around about now 12 minutes, since I lost some minutes, I will try to talk about the motivation of the project, or in short, motivation according to international shipping, then the research project itself, going over the project objectives, the fuels that we're using, that we used, and the research engine. Then I will show some results of particulate emissions of one of our measurement campaigns, and in the end I will finish with a conclusion and also an acknowledgement to all the colleagues that were involved. Yeah, talking about the motivation, I think it is really important what is the status quo in international shipping, and I will just go over this briefly because I think in the audience everybody is aware of the situation. But on the pro side, depending on what kind of source you're looking at, international shipping is responsible for more than 80% or even up to 90% of the global traffic. And if you just look at the diagram on the right side, also compared to other transportation sectors, international shipping, which is the green line in terms of CO2 emitted per transported ton and kilometer, is the most efficient transportation mode compared to others. If there's a pro side, we also have to look at a con side. The contrast of international shipping is that there are only global nitrogen and sulfur oxide emission limits. We have so far no global regulations on unburned hydrocarbons, on carbon monoxide, and as the focus of this presentation is on particulate emissions, also no global regulations on particulate emissions. Also, one thing that has to be kept in mind is that according to the sulfur cap of 2020, fuel change occurred. So we have also now on the market some fuels with different compositions compared to the fuels before. And if we burn these kind of fuels in engines, we have also changed emissions. Now I would like to go over to the research project. The general objective of the SARUS project was the reduction of ship-related emissions by optimizing and enhancing exhaust gas treatment systems. In this project, several sub-goals were defined. These were the optimizing sulfur oxide reduction and evaluation of particle separation of scrubbers, the evaluation and reduction of fine and ultrafine particles, as well as dust via filter technologies, Another sub-goal was the development of a 3D model for simulation of sulfur reduction and particle deposition inside the scrubber. And since we're using a scrubber, also investigations and optimization on the wash water treatment were in the focus in open and closed loop. For this presentation, I would like to focus on the first two sub-goals, especially from the first sub-goal, the evaluation of the particle separation of scrubbers. Why I would like to focus on that. When you look at literature or publications, you can find a high variation in the particulate matter reduction through scrubbers from no effect up to 90% of reduction. And this was then for us a hint to also look at this in our project. And then also, since we were trying to reduce the particle matter reduction via filter technologies, I also tried to show you with the results something from this sub-goal. Yeah, also, if we are looking at the separation of particles or the deposition of particles inside the scrubber, there are different factors you need to look at. For instance, the fuel that was used in other research work of other institutes. In our project, we used 6 kinds of fuels, a marine gas oil, and then also an alternative fuel oil. It was hydrogenated vegetable oil. This was just used for pre-investigations. For further investigations, we focused on the marine gas oil and then on heavy fuel oils. One of the heavy fuel oils was a compliant heavy fuel oil with a sulfur content equal or less than 0.5 mass% of sulfur. Then we had a standard heavy fuel oil with a sulfur content of 2.4 mass%. And also we were picking 2 highly aromatic heavy fuel oils, which we called blend A and blend B. Blend A had a low sulfur content, and blend B was had a sulfur content of 1.3 mass%. And the colleagues of the Chemical Institute that was involved also did fuel analysis with the Ghetti mass spectrometry, and then you can get nice pictures like you can see here. And what I just wanted to point out is if you use heavy fuel oils, or look at the heavy fuel oils, the amount of aromatic components increase. And especially for the 2 blends that we were using, what I was saying with the fuels that came up due to the fuel chain, to the sulfur cap 2020, is that we can find fuels that have high amounts of aromatic components, which also can then be found in the emissions on the particle matter side. Just to show you that from the heavy fuel oils, the amount of aromatics are increasing, especially on the blends. We were seeing high amounts of aromatic components. Then for the investigations, we were using a single cylinder research engine with 18 centimeters of stroke and 15 centimeters of bore. This single cylinder research and development engine is capable on running of a variety of fuels, from diesel over heavy fuel oils and other blends to alternative fuels. It is equipped with a common rail injection system and has an open engine control unit, and we can adjust the charge air and exhaust gas back pressure at this engine. And for our investigation, it was good that we can set up different kinds of exhaust gas treatment systems behind these research engine. From the test program, we were orienteering us at the test cycle E2 for heavy-duty constant speed engines for marine propulsion of the ISO 8178/4, and for the main investigations, we were focusing on the two test modes shown here in red. The first one of the test modes is test mode 4 for maneuvering operation at 25% of torque. For the research engine, it was a 20 kilowatt engine load point, and then also test mode 2 for open sea operation, which is the 75% torque, and here for the research engine, it was the 60 kilowatt of rated engine power. And we also used 4 fuels, 2 compliant fuels, the MGO for the SECA areas, and then the heavy fuel oil with 0.5 mass % of sulfur for the open sea, and then 2 non-compliant fuel oils. The highly aromatic heavy fuel oil was 1.3% sulfur, and then the standard heavy fuel oil was 2.4% of sulfur. Now, I would like to show you some results for the particle size distribution that was measured at test mode 4 in the maneuvering operation. 25% torque, 20 kilowatt rated power of the test engine. And what you can you see here, the black curves are the measured particulate matter emissions upstream the scrubber or the raw emissions, and then the green curve, the particle emissions downstream the scrubber and upstream a filter device, which was a wet electrostatic precipitator, shortly WESP. And the red curve then the particle emissions downstream this filter unit. And what you can see here that especially the HFOs which are non-compliant have higher amounts of particle number, or show higher amounts of particle numbers than the MGO and the compliant heavy fuel oil for the open sea. And also what is obvious is that you see when you compare the black and the green curve that a shift of the particle size distribution occur inside the scrubber. That's due to coagulation process inside the scrubber. So smaller particles coagulate inside the scrubber due to the extending residence time to larger particles. And then what we can see also in these 4 diagrams is that for MGO and the compliant heavy fuel oil, the reduction is there's no reduction. Just for the aromatic heavy fuel oil, the standard heavy fuel oil, we see a reduction via the scrubber, and then the main reduction is done through the WESP. If we look at the results from the test mode 2, the 60 kilowatt operation point, which is equal to 75% torque of the test cycle. One thing we have to look at is that MGO has a significantly lower particle number compared to the heavy fuel oils. And also here you can see, especially for the heavy fuel oils, the shift from the particle size distribution to larger particle particle sizes, but still through the scrubber we see a reduction, and the main or further reduction was performed through the WESP. Yeah, in the end, I will now come to the end with a conclusion. In the diagrams, I hope you've seen that the HFOs show a remarkable higher particle mass and particle numbers than compared to the MGO. Then when you look at the black and green curve, the scrubber led to changes in the particle composition. Also, we have seen that sulfur from the gas phase was partially transferring to particulate sulfate or particulate sulfate, where we've seen some increases in particle mass. I haven't shown this in particular, but that's an additional side information for you. What you've seen in the 4 diagrams on the 2 engine load points is that the scrubber affected the number size distribution of the particle emissions through coagulation of particles. And what we've seen also is that the inhalable particle matter fractions, which are identified as severe public health risks, are not removed. We still have large amounts of inhalable particle matter fractions downstream the scrubber. And with additional abatement systems like the wet electrostatic precipitator, we can reduce the particle matter emissions significantly. And but for the future, there are still further investigations necessary, since the system, the WESP, couldn't be operated at the highest voltage due to the duration of the testing. So for further investigations, the systems have to be optimized to increase the voltage to decrease the particle matter even more. And then thanks to all my colleagues who were involved in this project. And now I'm happy to answer some questions if there are some.
Okay, maybe I can. So first of all, thanks a lot, Mr. Etzien, for this very interesting presentation. Just a reminder to all of you to push your question in the tool. And maybe I will start with one question from my side. So can you say something regarding the dimensioning of this system compared to the cylinder displacement? So how much let's say the individual components are compared to the cylinder displacement? I know you are running the single cylinder engine, but just to give you a ratio of dimensioning to understand the proportion compared to, for example, to a DPF system.
Oh, okay. The scrubber was downscaled from the involved company Sake, and yeah, it's a pretty large tower compared to the engine. It is like it has an inner diameter of 30 centimeters, and it's a U-type scrubber with I think an entire height of the U-type of 2 to 3 meters. And then the filter components, I would say, like okay, it's compared to like the wet electrostatic precipitator was in size 1 meter with the entire cabinet, electrical cabinet was 1 meter times 1 meter times 2 meters height.
Okay.
From the dimensions. So compared to the engine itself, the exhaust gas treatment components were like the scrubber, I would say, due to the height twice times 2, and the WESP was the same size, like this, like the engine itself.
Very nice. Okay, then I have a couple of questions more. So what was the typical particulate size cut point of the scrubber?
You mean what it reduced, or
what was the typical particulate size cut point of the scrubber? So this is the question from the audience.
What does it mean? What is meant with the cut point?
I will give you the contact. You can answer directly. So we take it separate. Okay. Then regarding the WESP, how much electric power consumption have you measured this regarding the?
No, we haven't.
Okay.
I just can tell you that we were operating at 11 kilovolts. We were operating the WESP, and we could have increased the voltage, but then in the end we did this once, but then we ran into a limit of the system, and it shut down itself. But at this operation point for the audience, we were decreasing the particulate matter emissions down to 99%.
Okay. Okay.
So that's what I meant with further investigations with optimized systems.
Okay, maybe then the last question, can you also mention these results converted to number per kilowatt hour? So I think your results were referred not to kilowatt hour, but
Just try to. I don't think that I have a slide prepared for that, but
okay. Maybe I will give you also the contact then.
Yeah, that would be nice.
Okay, good. So I think this was all. Thank you, Mr. Etzien, for this very nice presentation. I think it's now the time to step to the next one. So the next presentation then it is given by Mrs. Kati Lehtoranta. She's a principal scientist in a research team called Emission Control and Sustainable Fuels at VTT in Finland. And today she will speak about reducing particle emission from marine engines, fuel choices, and technology pathways. Hello, so Mr. Lehtoranta, the stage is yours. Thank you.
Thank you.
So we can see still in the, you have to put in the presentation mode and then
Okay.
we can see the screen, by the way. Okay.
Now all good.
Now it's all good. Thank you.
Yes, thank you. Okay, so good afternoon to all. And I will continue in the theme of reducing particle emissions from marine engines. And I will start my introduction a bit more from the basics than the previous presentations. As we know, when we use any kind of fuel in a marine engine, we all know what we get as a result. We get the work done, and unfortunately also some emissions as a result of the combustion process. And since we never reach in practice a complete combustion, we have those incomplete combustion products like hydrocarbons, carbon monoxide, and soot, which we can also call black carbon. So these are the particle emissions. And then depending, for example, on the temperature scales, some nitrogen oxide formation happens, as well as depending on fuel sulfur level, the sulfur oxide formation. And obviously the soot or the black carbon is visible to us in certain instances, as can be seen from these figures also. It was already pointed out the previous presentations that there is a need for actions to reduce particle emissions from ships, and this figure from a publication of Hilkka Timonen et al. Represents quite nicely the effects that the soot, the black carbon has, and it has both effects on human health as well as effects on the climate. The health effects come mainly, or the critical point here is the particle size, since these are small size particles, so they can penetrate deeply to human lungs and cause different diseases, asthma, premature deaths. And in addition to these effects, soot has effects on climate. So there are different kinds of effects. So when these particles are in the atmosphere, they can affect to direct absorption. They can have take part in the cloud formation, and since these particles stay in the atmosphere for days, even for weeks, they can also be transported over rather long distances. And one critical issue here is the Arctic areas, where you have white snow, and then if you have in addition a layer of black carbon on the snow, you can easily understand the effects it will have on the snow and ice melting processes. So important effects it has. Then, since I like to simplify things, if we want to do something, and what we already heard in the previous presentations, since we have there basically only the engine and the fuel, if we want to change the exhaust gas composition, we need to do something for the engine or something for the fuel. This is as simple as it is, putting it in a simple way. If this is not possible or enough, then we can introduce some after treatment device so we can treat the emissions after they are formed to get those low emission levels. So today we all know we have already regulations for these global regulations for the nitrogen oxide and sulfur oxide, and this is also where we start with, which forms the basis for the conditions when we start to think of reducing the particle emissions. And it is especially this fuel sulfur level limitation that has a huge impact here. So when one is thinking of the particle emission reduction technology, it can only be selected once the choice to fulfill the sulfur legislation is adopted. And today I will shortly present these three different pathways. We actually already had these two presentations for two of those, and now I will show some more. So the first one is when we have chosen distillate fuel to fulfill the sulfur legislation, and we add there a diesel particulate filter. The second one is when we choose gas, natural gas for fuel that is nearly sulfur-free, and in trying to rely that the gas combustion is known to produce lower particle emissions, we study that without any after treatment. And then third one, when we utilize this high sulfur level heavy fuel oil in combination with the scrubber, and then add there an additional filter technology. With all these three studies, we have conducted these particle measurements, also many other gaseous measurements, but I will only concentrate to these particle measurements today. So the particle mass measurement according to this ISO 8178 standard method, then the particulate number, also according to this standard that considers non-volatile particles with the diameter greater than 23 nanometers in size. And then in addition to this, we have also measured the black carbon. Then to these three concepts and results. So first one was the distillate fuel combined with the diesel particulate filter. All of these projects we have run in different engine laboratories. So this one was at ABC with the 2 megawatt medium speed engine. And here we had an active regeneration DPF. So when we have had for a long time these DPFs on the roadside, and in general in those there is a passive regeneration, meaning that there is a catalyst which is helping the regeneration, but here we have an active regeneration without any catalyst. And in combination with this, we have an SCR for the NOx, nitrogen oxides reduction. In this slide, I show shortly the results of these experiments, now the particle emission results. So first of all, in these figures, in the x-axis, we have here the cycles. So with this setup, we have been measuring the whole emission cycles. So behind each of these bars, there is several load modes that have been run, and then the result calculated according to these standard methods. And with the blue color, we have here the engine out emission, and then with the green, the one that is measured downstream of the DPF. And 3 different cycles run with this. And it's easy to see here that these both PM, so mass emission, and PN, particle number emissions, are significantly decreased by the DPF. And in the PN, we have here the logarithmic scale. And when we look at the PC result, we see, or we do not see, any black carbon here. So the levels were very, very low in practice. We got no black carbon out from the DPF. And these results, according to these PM and PN, which are regulated for example, in this EU regulation for inland waterway vessels. So these are fulfilling those regulations. And just to note that will not show any results, but when in combination with the SCR, also the NOx levels were achieved with this concept. Then to the second project or study. So this was done with the natural gas as a fuel in VTT's laboratory marine engine, 4-stroke medium speed diesel engine run in dual fuel mode. So we had the natural gas as the main fuel, and then we had this very low sulfur level marine gas oil as the pilot fuel. And in comparison, we also did studies with marine diesel oil, which fulfilled this sulfur limitation of 0.1 in this study. Similar chart presenting the results, although now only in 2 different load modes. So no full cycles were studied in this case. With blue, we have what we get when we run the engine with this marine diesel oil, and then with green, what we get when we run it with the natural gas. So again, we see huge differences. We see that both the PM and PN levels are significantly lower with the natural gas use compared to the marine diesel oil use. And here in the black carbon, it's again very difficult to see anything, any black carbon coming out of the natural gas combustion. So in practice, there is nothing. If we like to compare to the limit values for this EU's regulation for PN, I have named here the limit value 10 to 12, and based on these 2 load modes, we are close to that, but obviously you would need to run the whole cycles to see where you are. Not going into other emissions today, as said, but just to note that with the natural gas combustion, you have the methane slip challenge that needs to be solved. Then the third case, so the high sulfur level heavy fuel oil in combination with the scrubber, and then having an additional filtration technology for particles. Our test fuel here was having sulfur of 2.75%, and the test setup was built up in connection to a medium speed diesel engine. So we had a wet scrubber with alkali dosing, and then we had a wet electrostatic precipitator here. So the electrostatic precipitator consists of these charged electrodes and collector tubes. So the particles are electrically charged, and then they are collected on the surfaces of those collector tubes. I will not go into any details of this, and this is something that, as I mentioned here, that is to be published later on. So again, similar result slide from this setup as well. Here we have now 3 different load modes as an x-axis. So not cycles in this case, these 3 load modes were studied. And then I have 3 different bars. So here I have started from the engine out. And then with the blue, I have the scrubber out emissions. And then with the green, what is coming out of the WESP system then. And what we see in PM, also in PN, and also in black carbon, when we look at these green bars downstream of the WESP, that in all these studied conditions, the system was working very well with very high reduction efficiencies. And in practice, I have enlarged these PM and black carbon charts here, so there is very small amounts again. So in practice, no black carbon either out from the WESP system was seen in these studies. Noting the other emissions here, so scrubber is dealing with the sulfur, WESP with the particles, then noting that you would still also need to deal with the NOx emissions, for example, with an SCR. To conclude, and this is also conclusions that 2 of those can be made based on the previous presentations as well. So with all these systems I shortly presented today, we can achieve significant particle emission reductions. So when we know that these particle emissions have both impact on the human health and climate, and know that we would have direct benefits of reducing these particle emissions also from the marine engines, we now also know that we have technologies, some already available for the DPF system that was involved in our project. It already has this EU stage 5 and ultra low emission vessel certification, and then others are also available, developing so that we can decrease the marine particle emissions. I would like to acknowledge all my colleagues working at different engine laboratories, and thank you for listening, and I'm here to answer questions, and you can also email me later if you have something.
Thank you, Mrs. Lehtoranta, for this very nice presentation and also very good technology comparison. So maybe again I recommend to pose your question in the tool. In the meantime, maybe I can do one question from my side. Can you comment about the regeneration strategy of the first system, of the DPF system? So how much? So you said it's an active regeneration. So do you build? So can you comment how much was energy intense? What is in the CO2 balance of the complete overall consumption? If you have measure how much effort you have to put to regenerate?
Yeah, there's a procedure for that, of course. On this slide, you can see one publication that is done from this. I would advise you to take a look at that, what you can get from there. But there is also procedures, since these measurements were done following the standard methods, the standard cycles, the results were calculated according to those. So any extra effort or energy that is needed for the regeneration is taken into account into calculating the final results.
Okay. Then I have here a question for the audience regarding the methods, the measurement methods used in the study. So they say that the IMO's black carbon measurement methods are discussed. So can you mention in which methods were used in this study regarding, so that let's say for the black carbon measurement?
Yeah, for the black carbon measurement, we had here the microsoot sensor. So as far as I know, this is fulfilling the IMO's black carbon definition.
Okay. Other question from the audience? Otherwise, I will do my last question. Do you see the possibility that the particulate matter will be introduced in the upcoming IMO legislation? What is your opinion in this respect? So like it is now in stage 5 for a highway. So do you think that the upcoming IMO legislation, this will also be introduced, or will be just an additional requirement for a specific vessel type approval?
Since the black carbon issue has been in discussion already so long time, I would expect to have some limit for the black carbon especially.
Okay. Okay, so I think also look into the time. I think that's all from this session. And so thank you again for this very nice presentation, and thank you for the answers. So then we go to the fourth speech of today, that is given by Mr. Fabian Kock. He is head of the section Environmental Technologies, Air Technologies at DNV, and he will speak about the best practices for compliance today. So Fabian, the stage is yours, and then please, for the audience, put your question also in the meantime of the presentation, and at the end we can do some Q&A session. Thank you.
Yeah, thank you, Stefano, for the kind introduction. I hope you can all see my presentation now.
Yes, it's very good and everything fine.
Okay, thank you. Yeah, in my session actually, which will close this tech talk for today, I will actually talk about decarbonization and reduction of greenhouse gases. First of all, I would like to give you a only short introduction into the regulatory background at IMO. And then for the rest of my presentation, we'll only focus on the so-called EEXI, the Energy Efficiency Existing Ship Index. Only shortly, the end of this long day, maybe only shortly into regulations. I would like to start with some regulatory background, however, I'm not really going too much into the details here, but I believe it is worth to show that these short-time measures by IMO, the EEXI and CII, are only a beginning of a longer story on greenhouse gas reduction imposed by IMO, which I believe most of us will be faced with for the next couple of years, maybe even up to our retirement. So the short-term measures are illustrated here, one of which is development of technical and operational energy efficiency measures for new and also now existing ships. And also maybe good to point out here, life cycle analysis of fuels. On top of that, there's midterm measures and also long-term measures. And in my presentation, I will only now focus on the development of technical and operational energy efficiency measures for new and existing ships. And these are now regulated. And in short, they are the EEXI, which is a technical measure, and an operational measure, which is the CII. First of all, let's look into the EEXI. That is the Energy Efficiency Existing Ship Index. That is nothing else than an extension of the well-known EEDI, the Energy Efficiency Design Index of ship. In short, it is nothing else than a specific CO2 emissions of a ship. So it is the engine power multiplied by fuel consumption, specific fuel consumption, and then defined CO2 factor for the respective fuel. Then innovative technologies which reduce CO2 emissions can be deducted. And that is then basically divided by reference speed capacity, which is in most cases the dead weight, and several correction factors depending on ship types and so on. Now, the important thing is that the EEDI and also the EEXI, which is now also applied for fleet and service ships, is only calculated once in a lifetime. So there is only a one-off thing to do if no bigger major conversions are done to the ship or the energy efficiency of the ship is significantly improved. And like NOx emissions, the EEXI is based on standard reference conditions. So it's kind of like you can compare it somehow to the automotive industry, where also the fuel consumption, you might know about the NEFZ test, is measured under reference conditions. So similar here now applies also for the EEXI. The EEDI, as I mentioned, has already been applicable for new buildings since many years, since 2013. And the EEXI is now an extension of this regulation, and it is to be applied to all ships in service, depending on ship sizes, ship types, and so on. I will come to that later. And most importantly, ships will have to comply with the EEXI by the end of 2023. So that is by the end of next year. That is the first periodical survey in 2023. Ships will have to comply with the EEXI requirements. And this is also worth to mention here, the EEXI is only to be approved and surveyed by the ship's class society or recognized organization of the ship is flying. Only one slide maybe on CII, only to illustrate the differences here. The CII is an operational measure. So, if you again compare it to the automotive industry, that is not the NEFZ fuel consumption, that is actually the in-use fuel consumption, how you operate your vessel or your car, okay? And that is purely based on reporting of fuel oil consumption data, which is done on an annual basis anyway. And then based on this fuel oil consumption data being reported by the owners and the distance traveled, the CII is calculated on an annual basis, and there will be a rating. And depending on the ratings, ships have to react and implement mitigating actions in case they do not comply with the required ratings over the years. So back to the EEXI. So again, this is a design measure only to be calculated once in a lifetime and certified under reference conditions. If you take a closer look at into the formula again, then you can see here what the biggest influencing factors are. So that is on one side here, of course, machinery, engine power, fuel consumption. Fuel consumption, I believe, the potential to further reduce fuel consumption is marginal. However, here the CO2 factor, so that is the fuel actually used under design conditions, again, has a big impact on the EEXI value. And then on the other side, also, of course, the reference speed. So that is more or less the hydrodynamics. Some more background maybe on the applicability here. Don't be shocked by this chart here, which I'm presenting. But this only illustrates that IMO defined ship types for MARPOL, and the required EEXI then is depending on the ship type and the capacity or dead weight, or here also in some cases even the gross tonnage, defined reference lines for the required EEXI values, which is the minimum values which have to be fulfilled by an individual ship. We also see that for certain ship types, the EEXI is not applicable. It is worth to note, however, that the CII rating has different applicabilities. So if your ship does not require to report an EEXI, it does not automatically mean that it does not have to report a CII rating. So please take a closer look at here the applicability charts. One question we are commonly faced with is actually if a ship does not fit into one category. So if, for instance, if a ship can, according to the definition, be categorized as bulk carrier or general cargo ship, then also the regulation is clear. Ship must be under this EEXI regulation, must be categorized under the most stringent, meaning the lowest required EEDI and the lowest EEXI. A few minutes ago, I mentioned that the EEXI is an extension of the EEDI for the fleet and service ships. So now you might ask yourself, does it also apply to new buildings? And here's a clear answer, it is yes. So ships will have to comply with the required EEXI values on the first periodical survey in 2023, however, also on the first initial survey, so that is the delivery. And now you might ask yourself, okay, but vessels also have to comply with the EEDI. Well, why am I mentioning this? Well, thing is, the reduction requirements for EEDI and EEXI are not aligned. The EEXI is actually more stringent than the EEDI. So dependent on the contract date and delivery date, a vessel like, for instance, here, this bulk carrier might fall under the EEDI requirements for phase 1 only. However, if the vessel will be delivered, say in March next year only, it will have to comply at the time of delivery with the required EEXI also, which is more stringent than the required EEDI. So please keep that in mind, that EEXI is more stringent in most cases than the EEDI, and will also have to be complied by the ships under construction now. Okay. What are the countermeasures? How can the EEXI values, mostly for the fleet and service ships, be improved? I tried to illustrate already with the formula, which I shortly illustrated by these blocks which I showed. But this only gives you some ideas about the potentials. The biggest potential, and that is also what we see now so far, is applied in most cases, is engine power limitation. So for instance, just an idea here, just if the engine power limitation is reduced by, say, up to 50%, that will result actually in EEXI improvement in the order of 37%. A big improvement also has a fuel switch to alternative or fossil-free fuels. Fossil-free fuel, like for instance, let's say ammonia, even will have an EEXI of 0. However, ammonia engines are not yet available, so some ship owners already constructed ships with LNG as fuel. And here you also see that not only a specific fuel consumption improvement is achieved, but also due to the difference in this fuel conversion factor to CO2, an EEXI improvement in the order of 25% can be achieved. However, conversion of a diesel ship to a dual fuel ship is quite costly and also might take some more time. So we have seen a couple of conversions, but what we see most for the time being in order to comply with the EEXI is actually engine power limitations. All the other measures here you see here, like rotor sails or energy saving devices, like for instance ducts or other measures, are marginal. IMO, however, also allows for other innovative technologies. However, they are still at an early stage. Some ships already apply those, photovoltaic cells, for instance, or wind assistance by Flettner rotors, but those are only marginal on the in actual construction now. But I believe we have to see more than those in the future in order to comply not only with the EEXI requirements, but all these measures will also have a direct effect on the CII, of course. Only shortly, maybe coming to the most effective measure, maybe, or most prominent measure, which is now applied for the EEXI compliance, that is so-called engine power limitation or shaft power limitation. Engine power limitation is a limitation of the power of the engine, which is actually limiting here, whereas shaft power is based on measuring the torque provided on the propeller shaft, and then in a closed loop limiting the engine power based on the measurement of the torque. You can identify different functions now for these EPL and Sharpoli systems, and DMV now also offers a type approval for these systems. You might have seen at SMM last week we presented actually 2 type approvals which fulfill or part of these functions, or maybe even all of these functions. So there's power limitation, override must be available due to requirements of emergency cases. An indication should be given, alarm, and the recording of the override events, of course, should also be available, and the system should be so-called tamper-free, so the crew should not be able to tamper with it without recording of any failure modes. Only one thing maybe to mention, that Ajax in the meantime also published an recommended practice for the shaft power limitation system. There's a slight deviation between the requirements of MEPC and Ajax, because you can read also the Ajax interpretation that no feedback of the shaft power limitation back to the engine is actually required. And here I only recommend that the consensus with flag administration might be required in case you think of applying such systems. Only shortly, approval process. Ship owners are aware of that. DNV is offering not only a tool for the calculation of EEXI, but also for the submission of this onboard management manuals and submission of the whole process here. But please keep in mind, all ship owners and operators listening here, if you do some alterations to the engine or engine control system, that is not really related to EEXI, that is related to class rules and safety and SOLAS. If you alter an approved engine beyond its approved limits, then also other approvals beyond EEXI are applicable and required. So in case, for instance, you are fiddling around with the engine control system, this needs to be submitted also to class 4 reapproval. So please keep in mind that EEXI is not only a statutory requirement, but in cases you are doing some mitigating actions, might it be a propeller retrofitting, bulbous bow, or even engine improvements, keep in mind that those also have to be approved according to SOLAS and Ajax and class rules. This already sums up my short overview, with a short overview that DNV is also offering more information, webinars, technically newsletters, and so on this decarbonization pathway. And I'm now happy to receive some questions from you. Stefano?
Yeah, hello, Fabian. So thanks a lot for this very good presentation. I mean, again, I recommend to pose your question, but maybe I can start from my side. So there is a lot of pressure coming for this defossilization, of course, and different kind of fuels with different carbon content, origin of the carbon. So how this will affect the regulation? Do you will see that the regulation will take care about and how this will be deployed in the life of the ship? No? So if somebody, I don't know, green methanol, non-green methanol, so how this will be regulated, for example?
Of course. In my presentation, of course, I try to focus only on the EEXI, which I try to illustrate as a design measure. Mm-hmm. For instance, if you operate your vessel on biofuels, mm-hmm. that will have no effect on the design of the ship. Ergo, it will have no effect on the EEXI.
Okay.
The effect, however, on the operational measures, like for instance MRV, DCS, or the CII, that is still to be defined by IMO actually, but most probably will have an effect, of course, because that is part of this life cycle analysis of fuels.
Okay.
But you could say that if you do not have to change the design of the ship, then it will have no effect on the EEXI.
So practically the governing fuel is the one that is, let's say, assigned as a practical design fuel. So that the ship is designed for this fuel, and
actually, the regulation is simply referring to the parent engine NOx test.
Okay, okay, to the parent engine NOx test. Okay, so
it's not even the fuel which is on board of the ship. It's a fuel which was used during the parent engine test.
The parent engine test. Okay, very good. Okay, thanks. You were very clear. Let's say, okay. I think that from my side, I think we are also close to our time limit. So if there are no further questions from the audience, I would like to thank everyone to join this tech talk for today. And I would like to give back the word to Mark from CIMAC to make the final speech, and also to invite you for the upcoming tech calls that we will do. Mark, the stage is yours.
Thank you very much, Stefano, for your moderation and guiding us through today's session. I'm not sure, can you see my screen already?
Yes, we can see.
Okay.
Yeah.
Then I want to once again hint towards our upcoming Congress next week in Düsseldorf. Anybody interested in new upcoming hydrogen topics and talking to experts from the industry may find a good platform to form contacts and listen to the latest technological developments. And of course, I want to hint towards our next Tech Talk special, which is going to take place on September 27th. The topic is going to be engine components and basic research. And with that being said, I'd like to close the session for today. I once again want to thank all of our speakers for their time and the interesting presentations. I want to thank you, Stefano, for your time to moderate today's evening. And I want to thank all of the audience for participating in today's session. Thank you very much and have a good day. Goodbye.
Thank you.
Bye.
Bye-bye.